Alright, so here I want to illustrate the issue with the concept of numbers and how they don't quite correlate to how things really work. Alright, so here we've got a circle that's quartered, right? So we have four equal pieces. They're all squares. Circle's embedded in a square. And the way we conventionally find the area of the circle is pi times the radius squared. So one of these squares times pi gives you the circle, the area of the circle. And that relationship holds for ellipses. So we can stretch it, and the area of the ellipse is still pi times the area of one of these rectangles, right? So the area of the ellipse or the circle, doesn't matter, any ellipse, is pi on 4 of the embedding rectangle. Okay. So there's that. And it doesn't matter that we stretched it, right? So it doesn't matter if this direction is the same as this direction. Okay. What ends up happening is the expression becomes apothem sub x times 2 times apothem sub y times 2. Right, so this semi-major axis times 2 times semi-minor axis times 2. That gives you the rectangle, and then we're going to take pi of that. So you end up with a pi on 4 because of those 2's. Now, when we look at like the binomial theorem, we get situations where it's not necessarily cut this way, where not every single piece is the same. This is where we get a 4, but we could cut it like this, right? So now you're getting, so say this distance is a, this distance is b. This is a squared, this is b squared, this is a times b, this is a times b. So you get a squared plus 2ab plus b squared. And that's the binomial version of 4. And when we stretch it, it doesn't matter. This area is still the same as this area and different from these two areas. So we still get something like a squared. It's scaled vertically by the constant I'm using here. I'm calling it k. It's kind of my go-to. Alright, so here it's like k times a squared, kab, kab, kb squared. So you can just factor the k's out like they don't exist, and it becomes like this, right? Which is the same reason why when we scale this, it doesn't matter. It's still basically doing the same thing. It's still what we would normally call 4. But it's interesting that this scaling doesn't affect what 4 is, but this scaling does. All right. So in my in the expression that I'm using to find the relative area of a odd-sided polygon inscribed within a square, it's not the best equation. It could be better, but it yields results that converge on pi on 4, so whatever. Good enough. Sometimes the odd number polygons don't quite fit in the square. That's okay. They come close. Whatever. It still gives us some illustration of what's happening. What's happening there is you get an expression in the denominator that quarters the space this way, But the way that we're actually doing the construction, we're quartering the space this way, where the center of the polygon is at the intersection of this half and this guy. So it's usually more like up in this territory, right? And as the number of sides increases, it gets closer and closer and closer to this case, where it's perfectly quartered, like for the circle. And that's why in the limit, you do get a 4 in the denominator. It does turn into pi on 4, ultimately. But whenever there is an actual number of sides, it's something like this. Even though the equation in the expression in the denominator is doing this. So somehow these are more intimately related to each other, where we've got these two equivalent pieces and these two equivalent pieces. This type of quartering is more intimately related to this type of quartering than this type of quartering is to this type of quartering. Here we have a single term for this, 4. Here, that doesn't work. Here, that doesn't work. But this and this are interchangeable somehow. This is interesting. This is interesting. There's some point here where things are broken. And you also end up with, so like when you're a little kid going through school, right? Adults, like little kids, will say, well, you cut something in half, and it's like, oh, I want the big half. I want the small half. But the adults will say, no, no, the halves are always equal. This is interesting because historically in English, this is cutting it in half. 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 All of these, because we get two pieces, those are all cutting it in half. Doesn't matter. So very recent, and English is only like 1,000 years old as a language. Like, it's not very old. So it's very recent that half means this specifically. Similarly, it's probably pretty recent that quarter means this specifically. Right? You ask a little kid, how many pieces is this cut into? They'll say 4. Or what's another name for that? And they'll say, if they know the word, they'll say, yeah, it's in quarters. You cut it into quarters. An adult wouldn't say that unless it's like this. Now it's in quarters. Now it's not. So there's something really interesting in here, because the way that the numbers are set up, like by Giuseppe Peano and Richard Dedekind, carried through by Whitehead and Russell, and still accepted in framework of like Zermelo-Fraenkel's set theory. The symbol that is used for this is treated as if it works for this, but nobody will accept that it works for this. There's a fundamental problem here.